This is a walkthrough of Problem 2 on Practice Exam 1 of Module 6 in the book Problem Solving Guide for Mechanics and Thermodynamics. James wants to measure the muzzle velocity of his .357 Magnum, which fires an 8.1 gram bullet. He goes under a table, fires the gun vertically up through a hole into a 1 kilogram block. And the bullet sticks in the block, and the block rises 120 centimeters above the table. What was the initial speed of the bullet? We need a good diagram. There's a start, there's a hole in the table, the bullet goes through the hole, hits the 1 kilogram block, stays in it, and the 1 kilogram block flies up 1.2 meters. So, when the bullet sticks in the block, a significant fraction, as we will see, of the kinetic energy is transferred to heat. A lot of heat is generated. If we're going to get the right answer to the problem, we have to understand that we're going to lose a lot of kinetic energy to thermal energy. We can write the conservation of energy equation. The kinetic energy of the bullet is equal to the gravitational potential energy of the block and the bullet when they're 120 centimeters in the air, plus a tremendous amount of thermal energy. The problem with using conservation of energy is we don't have the thermal energy. So that equation is not going to help us. Let's use conservation of momentum for the collision between the bullet and the block, because momentum can't be transferred to thermal energy. So we're only using conservation of momentum during the collision. When we use conservation of momentum, it's almost always some small fraction of a second, just before the collision to just after the collision. The time it takes the bullet to stop within the block. So we have mv initial equals mv final. Initially, just the bullet is moving. We don't know the initial speed of the bullet. We're going to convert to kilograms. And then the bullet sticks in the block. The block is 1 kilogram. So the final mass is 1.0081 kilograms. And then we have the initial speed of the block and the bullet after the bullet stops inside of it. Two unknowns. So we have the conservation of energy equation from the initial situation to the final situation, but we're generating a lot of thermal energy. What can we do? We know the block went 120 centimeters upward. If something goes 120 centimeters in the air, you can use conservation of energy to figure out how fast it was thrown. So we're going to have a middle snapshot. We're not going to have just a first and second snapshot. We're going to have 3 snapshots. We're going to avoid the generation of the thermal energy, or it's going to cancel out. So we have this situation. The bullet stopped inside the block. The total mass is 1.0081 kilograms. This block is moving up at some speed, and the final situation is it's 120 centimeters in the air, and it's at rest. So we can calculate the initial speed. Yes, there's thermal energy there, which is why the bullet's red. It's hot, but it's there before. So this is gravitational potential energy and the thermal energy generated. This is kinetic energy of the bullet and block plus the thermal energy generated. These must be equal, and the thermal energy cancels out because it was generated before. So now we have the kinetic energy of the bullet and the block right here must be equal to the gravitational potential energy right here. And we can calculate that speed. It's 4.08 meters per second. So the speed of the bullet and the block after the bullet stops within the block is 4.08 meters per second. Now we can go back to our conservation of momentum equation. We're not worried about the thermal energy because we're using momentum. So here we have the bullet. That's just the bullet, 8.1 grams. That's the initial speed of the bullet. This is just after the bullet stops within the block. This is just before the bullet hits the block, just after the bullet stops within the block, a fraction of a second. We can plug in the speed of the block. It's 4.08 meters per second, just after the bullet hit it. Now we can get the speed of the bullet. We have one equation, one unknown. It's 510 meters per second to 2 significant digits. So let's determine the amount of thermal energy lost, just for completeness. We already have the answer to the problem. So let's calculate the kinetic energy of the bullet. It's got a small mass, but it's moving really fast, and we're squaring that. This is about 1050 joules, 1050 joules. Afterwards, we got about 12 joules. So we went from 1050 to 12, 98%, 98.8% of the kinetic energy was transferred to thermal energy during the collision. So this problem demonstrates how to split the problem into two parts. The final situation for the first part is the initial situation for the second part. So let's go over these three snapshots in detail. The first snapshot is before the bullet hits the block. That's the initial situation. We know how fast it's going now. The second snapshot is just after the bullet stops within the block. It's heading upward at 4.08 meters per second. We got a lot of thermal energy generated. There's some kinetic energy left in the block and bullet together. 12 joules, not much of the 1050. The third snapshot is when the block and the bullet are at their peak. Here there's gravitational potential and no kinetic. Everything stopped. So, what happened to the initial momentum of the bullet? The bullet has momentum here. Here, nothing's moving. Everything's at rest. Well, the problem is gravity is acting on this guy. Gravity is an external force. You have a force that's leaking into your system. It's not a closed system if you let gravity in there. If you want to conserve momentum, momentum's conserved, but you have to include the Earth in your system. If you just include this in your system, then, of course, momentum is not conserved in this system because there's a force leaking through into your system. It's not a closed system. So when you conserve momentum, conserve it only during the collision, just before and just after. That's the initial situation. That's the final situation. That's problem 2.